For an affine variety X, we saw that we can use the Zariski topology on X to decompose it into nice pieces in its irreducible decomposition or its decomposition into connected components. The next step is that the Zariski topology can also tell us something about the dimension of the space X. So this word dimension exists in different contexts, but in most of them you are given some kind of geometric space X, and then the dimension is an invariant, it's either an integer or sometimes it can be infinite. And in most areas, like for example, the dimension of a vector space in linear algebra, or if you have seen this lecture, dimension of a manifold in differential geometry, is defined by saying, well, that at least locally on your space in some small open subset of any point, the dimension tells you how many degrees of freedom you have. In other words, if you want to specify your position in this small open subset, like how many numbers do you need to fix in order to tell you the coordinates of where you are? So this is one way to define the dimension. And also in algebraic geometry, there are approaches to dimension like this, which we are going to see a bit later. But for now, we are kind of lucky because in algebraic geometry, a different way to define the dimension is to characterize it purely in terms of the topology of the space via the notion of chains of irreducible subsets. Let me first give you the definition, and then I'm going to say a bit about the interpretation and the idea behind it. Again, this is something which we can do in some more generality. In fact, we can do it a priori for any X, which is a non-empty topological space. Given this data, we say that the dimension dim of X is an element of the natural numbers union infinity, where the natural numbers include 0, the dimension can be 0. And this number is the supremum over all natural numbers, such that there exists a chain. So it starts with a non-empty set y0, strictly contained in y1, strictly contained in y2, and so on, up to n is the number of these sets, all the way contained in X. So this is a chain of length n, and each one of these yi should be an irreducible and closed subset of the topological space X. So just to give you an idea, if this is X, then you could, for example, take a non-empty set y0 just given by a single point. This would then be contained in an irreducible set y1, strictly contained, and then strictly contained in y2, which in this case could be all of X. So this would be such a chain, and then we would say this is a chain of length 2. And then in the context of this definition, this would tell you, since the dimension is the supremum of all of these lengths, it would tell you that the dimension of this space X, which I drew here, would be at least 2. So we'll come back to this in a second. Let me just kind of finish the definition by saying, if you are given now any non-empty irreducible closed subset of X, Y, then we define the codimension, codim X, Y, of this subset inside of X as the supremum over all n as before, such that there exists a chain, and now Y should be contained, possibly equal to y0 and then y1 and so on until yn inside X, again of irreducible closed subsets of X, which now should contain Y. So in this picture here, you could say, for example, y is equal to y1. So you already start with the red one. And then in this case, kind of the codimension, you can only go one step further until you reach all of x. So this would tell you, in this case, y1 has codimension 1 inside of this big space x. And at least, I mean, staring at this picture, I mean, it looks like y1 is something one-dimensional inside something two-dimensional. So maybe that would fit, that the codimension is equal to 1. So this is the kind of abstract definition. You can just parse it word for word. But the idea here is, and coming back to this picture, the idea here is that if you have something irreducible, like y0 inside y1, strictly contained, then this inclusion and the irreducibility force the dimension, whatever it should be, would force it to go up. You cannot have a strict inclusion of a 5-dimensional irreducible thing in a bigger 5-dimensional irreducible thing. And so these inequalities would tell you in each of these steps, the dimension should go up by at least 1. And so, of course, if you can take n strict inclusions, the dimension should be at least n. And then in an ideal setting, you would hope that, in fact, if you get a chain of maximal length, so a chain which cannot be extended any further, then it should satisfy that this dimension goes up by exactly 1. And then this would be the case where the dimension of the yi is equal to I. And at least somehow pictorially here, from what I drew, while the dimension of a single point, or in general dimension of a finite set, should be 0. So y0 has dimension 0, then y1 has dimension 1, y2 has dimension 2, and there it stops because you have reached the entire space X. So that's the idea you should have in mind behind this definition. But I mean, in general, I mean, even without this idea, this is a well-defined definition. It uses this notion of irreducible, which we have developed. And I wanted to make some sanity checks and I guess some insanity checks, because some things which you might expect to hold actually don't hold. So the basic sanity check is that when you have x equal a1 with the Zariski topology, then we have already seen the closed subsets of a1 are a1 itself and then the finite sets. And if you also require the subs to be irreducible, we have seen a finite set with more than one element is not even a connected set. So certainly it's not irreducible. And so the closed, irreducible, and non-empty subsets are just these singleton sets, the subsets having exactly one element. And, well, one thing that one should never forget is that also A1 itself is, of course, closed and irreducible. And so these are all the sets which we have available for making these chains. And, well, then there's basically just one type of chain which you can do. You can choose y0 to be one of these singleton sets contained in y1, which is the entire thing. And here you see somehow, because of this irreducibility, there's no bigger set than the singleton set except for the entire thing. Because, I mean, the finite sets would, of course, be bigger, but they're no longer irreducible. So somehow the dimension is forced to go up by 1 in this case. And so we have this chain, and it is also the longest chain. All of the maximal chains have this length. And so the dimension is equal to this index here, 1. So dimension of A1 is equal to 1. So this is certainly nice because, I mean, I have probably also said a couple of times before, take the one-dimensional affine space or the n-dimensional affine space. So this makes precise, at least in the case n equals to 1, that this is indeed a dimension. Now, you might have a very, on the face of it, good idea to say that, well, this dimension, here we defined it to be in n union infinity. And the reason is that we take a supremum over such length of such chains. And so this becomes infinity, the supremum, if you can have longer and longer chains, and there's never any bound. You can always find a longer one. Then you would get an infinite dimensional space. And you can imagine infinite dimensional spaces are hard to deal with. Now you might hope, having seen this definition of Noetherian topological spaces, maybe it's true that if you have a Noetherian topological space, it has finite dimension. I mean, certainly there was some kind of finiteness condition which says you can't have an infinite decreasing sequence of closed sets. But the issue is here we have kind of increasing sequences, and in fact, it's just not true that for such a Noetherian topological space, the dimension is always finite. It's not the case. And here's a kind of fun exercise which gives you a concrete example. And here we go to a topological space which is kind of constructed by hand, but it is very easy to see what it is. So somehow X, just as an underlying set, is the natural numbers. And we declare a set is closed in there if, well, it couldn't be the empty set, it can be the entire thing. These we always have to have. Or it could be a finite set of the form 0, 1, 2, 3 until some number n. Okay, so this is the claim that this gives a counterexample. And the exercise has kind of three parts. The first is that this curly C, which I specified here, indeed gives the closed sets of a topology on X. The second is that this is a Noetherian space. So you can think again, what was the precise condition of Noetherian, and then check it. And the second is, or the last part is, that the dimension of this space, with the definition that we gave before, is infinite. And so, unfortunately, it's not the case that any Noetherian topological space has finite dimension. However, as a sneak peek, next time is about affine varieties, and there we're going to see there it doesn't go wrong. Indeed, there we have finite dimension, and why that is, we'll see in the next video.